Welcome to University Educational Services Radon Training Program. I'm Dr. Paul Houle, and I'll be your guide in this program, which satisfies the course requirements for radon training in Pennsylvania. We will begin with a brief historical overview of the radon problem and a survey over much of the radon arena. So for the next 20 or 30 minutes, this is what you're going to see. But before we begin with that part of the program, I just want to say a few words about the program itself. You have a text along with this video, and you should have that text open to the very first page of the text. You will have in there visuals which you will be seeing on the screen, and you should always have the text opened to the same visual that you see on the screen as I discuss it. This way, if you want to make notes, you can do so right on the visual that's appropriate. Also, periodically, every 10 or 15 minutes, I've placed an array of questions which will follow in the appropriate place in the text, which I would like you to answer. And I'll point those out to you as we go along through this program. The purpose of those questions is to reinforce in your own mind the things that you have just heard. And they're an important component to the learning process. So please don't skip those when you get to them. Execute those questions and work out the answers. After you've done all of the questions in a given set, and there are generally between 5 and 10 questions per set, you should look in the back of the text. And in the back of the text are the answers to those questions. So you can confirm your answers, and those that you don't get right, you can see what the correct answers are. That's a good point, too, to go back into the text or perhaps rewind the video and look at that a little bit more to reaffirm the information that you may have misunderstood on the first pass. Also, as part of the program, to complete the program, we will be mailing indirectly to you, as I'll explain here in a second, an exam. And the purpose of that exam will be to confirm that you've watched the videos and worked your way through the text as well. Now, the way you will get that exam, since it's not in your current package, is to notify us who a proctor will be for that exam. Now, we will accept as a proctor for that exam any educational instructor. Now, we would prefer a university professor or a community college teacher. A high school teacher would be acceptable as well. It will be your responsibility to go to your local community college or university and identify a professor who will be willing to proctor the exam when you take it. You will notify us on that form, you'll see the form in your packet, who that proctor will be, and we will forward that exam to that proctor. You and the proctor can schedule whatever time you want to take the exam, and you will have 3 hours for that exam. It shouldn't take you 3 hours, but we are allowing 3 hours. When you're done with the exam, the proctor will mail it back. And we have a set of proctor instructions that will be sent out with the exam to the proctor. Now, the purpose of that exam is solely to confirm that you have watched these videos and that you have gone through the text. That's all. That is the function of that exam. It is not the EPA R&P exam, which you must also pass in order to become certified in the Commonwealth of Pennsylvania. This course will do two things for you, we hope. One is give you a very good understanding of the radon problem and all its avenues, and it will also prepare you to pass the R&P exam. When you're done with the entire course, and probably before you take the course exam, not the R&P exam, you'll probably have an array of questions. You should write those down and call us. We'll be happy to answer all of the questions that you might have. And I think that's pretty much the entire administrative picture. So let's begin with the historical development of the radon issue. In front of you, in your text, you should have this visual. And it starts off with the U.S. became aware in March of 1984. Now, what I mean to say by that is not that radon became a problem, a health hazard in 1984. In fact, radon was known to be a health hazard much earlier than 1984. 30, 40 years ago, radon was known to be a health hazard in mines. But in 1984, it became a household word. In that particular year, a fellow named Stanley Watrous, who works at one of the nuclear power plants in Pennsylvania, or at least did at that time, I don't know if he still does, but he did then, was setting off the radiation monitors in the power plant. Now, most of these nuclear power plants, in fact, all of the nuclear power plants, are required to have monitors so that when the workers leave the plant, they can be monitored for any radioactive material that may have been deposited on their persons. And if they leave the plant by passing through these monitors, if the monitors are not activated, then the individual doesn't have any material on them. Now, this particular individual, Mr. Watrous, was setting these monitors off on the way into work. Eventually, the problem was discovered to be in his home, and that finally it was determined it was radon gas that was the problem. The concentration in Mr. Watrous's home was so high that it was the equivalent, as you see here, to tens of thousands of X-rays for the occupants. So he was under a very high, he and his family experienced very high exposures. Once that event occurred, then it quickly became known that radon gas can be a household problem. And of course, as you will see, it certainly has become so. And currently, the EPA estimates that 1 out of every 15 homes have elevated radon levels. That's about 7 to 8% of all the homes in the United States are expected to have radon levels higher than the outside radon concentrations. Now, the way we approach the problem here at East Stroudsburg University was we first went and did a library search, and thanks to automation and computerization, we were able to search literally thousands of journals to deal with that might deal with the radon problem. In the process, we have discovered, and here's a typo in this overhead, this should be Sweden, has determined that 40% of its cancer deaths are radon related. We've also found that Mexico found high concentrations of radon and has attributed them to houses built from volcanic rocks. Now, let me just touch on where radon comes from. Radon is part of a large radioactive decay chain whose parent, the immediate parent to radon, is radium, and the ultimate parent, the precursor of all these radioactive elements in that decay chain, is uranium. And you can find uranium anywhere in the earth. In some places you find a higher concentration than in others, but fundamentally anywhere you look you'll find a certain amount of uranium. And some materials, as you pull them out of the earth, in this particular case volcanic rock, has more uranium in it than other kinds of material. And if the house is built out of this volcanic material in this case, then the uranium eventually becomes radon, or decays down to radon, and that radon is a gas. It is the only gas in the entire decay chain, and that gas can escape from the rocks and enter the house. And that's how Mexico has attributed their radon problems. But anyway, we see here that Sweden and Mexico have found radon problems. Further review of the literature, we found Costa Rica, India, Hungary, Austria, the UK, and many others found concentrations of radon in buildings higher than what it is outside. In fact, any country that we investigated had identified radon as a health hazard in their own country. The upshot to this is that radon is not solely a problem here in Pennsylvania or in what was originally called the Reading Prong, down around the Reading, Lancaster area. It is not only a problem on the east coast of the United States or in the United States alone. It is a planet-wide problem. Every country has seen radon as a health hazard, every country in any case that we have investigated. So the planet as a whole has a radon problem. Typically, the radon percolates up from the ground. It is predominantly a soil gas. It percolates up from the ground and gets dissolved into the atmosphere. And its concentration is so low at that point that it is not any kind of health hazard. The problem occurs, of course, if you build a house on top of a location where the radon concentration is relatively high. The gas percolates up, enters the house, and is captured by the house. It doesn't get dissolved by the entire atmosphere. There, the concentrations can tend to grow to levels that are, in fact, hazards to the human health. Outside radon concentrations, as you see here, are approximately 0.4 picocuries per liter. We're going to be talking about that unit in much greater detail a little later on in the program. And the most common unit in which we measure radon concentrations is the picocurie per liter, whatever that is at the moment. 0.4 is the outdoor average. So if we could get concentrations down to 0.4, we would be doing very well. It will be close to impossible to get radon concentrations in homes to less than 0.4, since the outdoor air is already at 0.4. Could be done, but it would take superhuman effort and would no doubt be uneconomical. For just a minute, I want to discuss the two predominant units for radon measurements. And as I point out just a second ago, the most popular unit for radon measurement is the picocurie per liter. And you see here that 1 picocurie per liter is equivalent to 2.2 radioactive decays per minute in a 1 liter volume. Now, there are a couple of things there that I want to spend a second on. One is, what do I mean by a radioactive decay? If you take an atom, and if it's radioactive, and you leave it alone, you just put the atom right here, after a given amount of time, the thing will decay. It will explode, in effect. And that we call a radioactive decay. It'll do so spontaneously. And there's very little that we as humans can do to impede that decay process. Now, I think everybody knows what a 1 liter volume looks like. I've got this bottle of seltzer water here. It's a 1 liter bottle, and you get some idea of what a liter is. It's roughly a quart. And so if I were to look in this bottle, and if I could detect with my eyesight, we can't, but if I could detect with my eyesight the radon that's in here, and if I saw 2.2 radon atoms decay every minute in this 1 liter bottle, then I would say that the radon concentration in this bottle, at least at this time, is 1 picocurie per liter. Okay. Again, we're going to see that unit, and we're going to have a more intense discussion of that unit later on. Another common unit in the radon industry is the working level. Now, the working level doesn't measure radon concentration specifically. It measures what's left over after the radon has decayed. Again, we'll get into greater detail a little later on, but you should recognize, at least for the moment, that 1 working level is equivalent to approximately 200 picocuries per liter. So the working level is a very large unit. It's a big item. And it's just another way of measuring the health hazard due to radon and the things left over after radon decays. The government agency, as you well know, involved with the radon issue is the EPA. And the responsibilities of the EPA, which I believe have been well met, as you see here, is to identify geographic areas that may have susceptibility to radon concentrations, and to establish guidelines by which we will deal with these radon concentrations. As you have already heard, the geographic issue is pervasive. In almost every locale where radon has been measured, it has been found to exist, and at concentrations in homes that are potentially hazardous to our health. So I want you to understand that all geographic areas are susceptible to the radon problem. Some more so than others, but effectively there is practically no geographic area wherein radon is not an issue to be dealt with. And as you will see as we go through the Citizens Guide a little later on, that the EPA has established very concisely a set of guidelines by which we will measure radon and by which we will decide whether or not to mitigate a radon problem in a given home. Now, there are lots of ways to measure radon, lots of detection measurements. Now, unfortunately, the human is not a particularly good measuring device for radon. We can't see it, it has no odor, you don't hear it decay. None of the human senses are important in the issue, and so we have relatively indirect measurement techniques. Here in this visual, I've delineated the times over which different measurement techniques can be used. Grab sampling occurs over a period of several minutes. Now, the way that grab sampling works in the radon business is simply this, that you go into a home, you have a device not unlike a 1-liter bottle, a little more sophisticated than this, but you have a device sometimes called a Lucas cell, and what you do is you draw air into that device. You take a sample of the air in the house. It takes a few minutes for this to happen typically. And then you take this sample of air to a laboratory. Sometimes you may have very active equipment that can actually sample and detect the radon gas in the air through this grab sampling technique. It's a device you can bring right into the building, a continuous radon gas monitor. And you'll see one of these depicted a little later on when we have a representative from the Pennsylvania DER describe how they work. He has some equipment with him. But it only takes a few minutes to sample the air and determine the amount of radon that's in it. And that's called grab sampling. Charcoal detectors were really the most popular, and in fact, even to today, are still the most popular detection mechanism, and they are deployed typically from 2 to 7 days in the home. Now, I have a sample of a charcoal detector right here. All it is a can, and it carries somewhere between 25 and 50 grams of charcoal. You bring it to the home, and in order to deploy it, you just pull off this cover aluminum foil, and you put it in the appropriate place in the home. Location we're going to talk about again later on. Charcoal, as you know, is a terrific absorber of almost everything. Odors, organics, etc., and radon as well. And so the charcoal absorbs radon gas, if there is any in the room, over a period from 2 to 7 days. At the end of that time period, you cover the detector and you return it to the lab. The laboratory has a technique by which it can analyze how much radon gas has been absorbed in the charcoal, and therefore what the concentration must have been in that particular room as an average value over that 2 to 7 day period. And this is, without question, the most common measurement technique, the charcoal detector. Other kinds of charcoal absorbers is this small vial, which carries 3, 4, maybe 5 grams of charcoal, and it works just like the charcoal canister. To activate it, well, this one is activated already, and you probably can't see it, but there's a little hole in the cap, and the radon diffuses down through the hole and into the charcoal. Again, the charcoal absorbs the radon. This is sent back to the laboratory and analyzed there to determine the radon concentration in the room. And this is typically deployed from between 2 and 7 days as well. We have alpha track devices, and they can be deployed typically from 30 days to as long as a year. That is approximately a year. It could be a little longer than a year, a little shorter than a year. Now, the alpha track device most commonly looks like this, and inside this detector is a small plastic strip. Now, I've broken one of these detectors up so that we could see the plastic strip, and I don't know if you can see it here, but this little plastic strip is actually the detector. And what happens is, as the radon decays, if a radon atom right next to this plastic strip decays, the particles emitted during the decay, when the atom explodes, parts of it fly off in different directions, strike this little plastic strip, and amazingly enough, leave a scratch in it. The scratch is not visible to the human eye, and this has to be treated much like photographic film at that point. But in any case, the scratches get onto the plastic strip. You send this device back to the laboratory. The laboratory treats the plastic to make those scratches visible, and then they're counted. And the number of scratches is proportional to the radon concentration. The nice thing about the alpha tracks is that they can be deployed for very long periods. So if you deploy it for a year, you do get an annual average out of the measurement. Whereas charcoal detectors are short-term measurements, only 2 to 7 days. Further devices, as you see here, continuous working level monitors, continuous radon gas monitors. These are fairly expensive and complex devices which sample the air. You'll see one a little later in the program, but they're on the order of the size of a typewriter. And they're put in the building, they're plugged in typically, or they're battery operated. and they sample the air and make a measurement every hour. That is, they take an hourly average, and then they print that out. These devices have some uses. They are not typically used to monitor radon gas concentrations in homes as part of a very active business. More commonly, they're used for quick measurements to determine whether or not a problem exists in a very short period. And there are other uses for them as well. And you will again see the details of these devices later on in the program. And another device is the EPERM, which can be deployed from 2 days to several months. And in fact, I believe they can be deployed as long as a year. These devices, this is an EPERM unit here, and to activate it, you just open the device like this. Air passes down through this opening and into this cylinder, and inside the cylinder is the detection element itself. And there's a voltage applied to this detection element, and the voltage will decrease depending on how much radon is in the device. Again, details of this will be worked out for you later on in the program. Now, these are not all the detection mechanisms that are out there. It seems that every time I turn around, there's a new detection mechanism out. But these are, without a doubt, the most common detection mechanisms you're going to see out there to monitor radon concentrations. Some of the results that came out in, I would say, about 1988, 1989, were produced to a large degree by a faculty member at the University of Pittsburgh named Dr. Bernie Cohen. And in that time, he and I were in communication regarding some of the results. They were making measurements there at Pittsburgh. Measurements were being made here at East Stroudsburg University, and we were discussing some of those measurements. He forwarded to me at that time in 1989 some of the results that he had, some what he called preliminary results. And I have those here on this visual, and I call them the preliminary Cohen survey. And you see different counties, the number of houses measured in each county, and the average radon concentration found in those counties. Now, initially, if you look at these, you look at Cumberland County here, had 165 houses measured, average radon concentration found 9.2, which is a little bit on the high side. And all these other counties have concentrations much lower. And if we didn't know any better, we would guess, well, these other counties don't have as severe a problem as Cumberland County. But interestingly enough, the Cumberland County measurements were made predominantly in the cold weather during the winter seasons. And their concentrations were higher, and you'll notice they were roughly a little more than twice as high as the other measurements. This was one of the very first hints that measurements made in the wintertime would give higher values of radon concentrations than measurements made in the summertime. Now, today that seems, gee, of course, that makes sense. Radon is a gas. In the winter, the house is typically closed up pretty tightly, or as tightly as we care to make it, and the radon concentration can build up. In the summer, we have windows open, we have exhaust fans, attic fans, etc., many things which may bring in more outside air into the building. And the radon concentration would be dissolved more, and it would be lower. So this was a hint at the time that winter measurements would produce values higher than summer measurements, or any other seasonal measurement, in fact. As you can see on this next overhead, I've summarized this. In this comment, generally, concentrations are higher in winter than summer. Simply stated, that's only because we have more air exchanges in the summer than we do in the winter in a given house. Another thing that we discovered, measurements were being made in basements, first floors, second floors of homes, and we discovered, again, looking back on it, it seems only reasonable, but we discovered then that if you look at it, basements are generally have higher concentrations than first floors by a factor of about 3. In other words, if you have a basement concentration of 5, or let's say 6 picocuries per liter, typically the first floor would have a concentration of around 2 picocuries per liter. And then the second floor would have a concentration very much like what it is outside. Now, there are exceptions to this, and I've heard stories and have had people tell me that they have found radon concentrations on second floors higher than in the basement. And while I can see physically that that is possible, that is very uncommon. You should expect that a measurement which is made in a basement area that is close to the ground and has the least amount of ventilation in it, that the radon concentration will be higher than the concentrations in the other floors. Now, I note here a factor of 3. I can see a lot of variability to that. Maybe it's only a factor of 2, or maybe only a little bit higher. If a house has forced air heating, in other words, air is taken from the basement, heated, and then passed into the other floors, then in that case, I could see where the radon concentrations on the first and second floor could be as high as the basement. But typically, you should expect, since the radon is a soil gas, comes up through the foundation and then through the rest of the house, that you should expect concentrations on the lower levels to be higher than concentrations on the upper levels. Now, I want to backtrack for just a moment. The issue of the seasonal measurement, we've made some calculations that show that winter measurements tend to be approximately twice as high as summer measurements. And that's a number you may want to keep in the back of your head, that in the winter, radon concentrations in a given location will typically be higher, and we have found that there's some average value of about 2, twice as high in the winter than in the summer. Also, I'd like you to recognize that radon is a gas. I've said that several times. It's a gas. And because it's a gas, the concentration in the home is not particularly uniform. If you deploy your charcoal detector for, say, 7 or 8 days, say 7 days, and then you send it back to the lab and they send you back a result, the concentration is 5 picocuries per liter. That's the average value over that period. The radon concentration during that period can vary dramatically from hour to hour, and certainly varies quite a bit from day to day. So don't expect that the radon concentration in the house is approximately 5 all the time when you get a result like that. Sometimes the concentration will be 1, other times it could be 20. On the average over a measurement period, if you got a result of 5, then that's what it is. The average is 5. So you get lots of hourly fluctuations, you get seasonal fluctuations, etc. You even get weather variations. The atmospheric pressure, the air pressure on the surface of the Earth, whatever its value is generally just a little bit lower than what the soil gas pressure is beneath the surface of the Earth. That is, there are gases beneath the surface, and those gases, as I pointed out, are percolating up, radon gas being one of them, percolating up. Now, the reason it can come up is because the pressure under the surface of the Earth, and I'm not talking 100 miles down, I'm talking 10 feet down on that order, that gas pressure is just a little bit higher than the atmospheric pressure, and so that's driven up into the atmosphere. If you were to lower the atmospheric pressure more, say you get a low pressure area moves in, bad weather comes in. If a low pressure area comes in, then the disparity in the pressures is larger, and that higher pressure in the soil will drive even more radon gas up. And so you will find that in very poor weather conditions, that is, say, thunderstorms are passing through where the atmospheric pressure is low, that the radon concentration can spike up to values 10 times what it is when the atmospheric pressure is average. And so poor weather conditions cause the radon concentrations to get very high as well. Your detector, which is deployed for 2 to 7 days or 30 days or longer, etc., those are average values over all of these kinds of fluctuations. Now, I'd like to take a minute as to how we know that radon is in fact a health hazard. Radon, of course, is a radioactive element, which means, of course, that it decays spontaneously by itself given enough time. And when it spontaneously decays, it can do some damage to the human. Now, how do we know that? This is a fairly, or can be, a fairly slippery issue, so you'll need to pay careful attention. First of all, we know that there are health hazards to high doses of radiation. And if you see here on this visual, we have the mortality statistics of A-bomb survivors. The United States, as you well know, dropped atomic bombs on Hiroshima and Nagasaki, and we know how many people died from these kinds of exposures. Very high exposures, of course. We are aware that there are persons treated with radiation therapy that were damaged by that therapy. Initially, when radiation became popular or contemporary as a tool to help eliminate tumors and the such, it was not clear that in some cases we were doing more damage than we were doing good. We do have that data. We also know the effect of radiation on uranium miners in poorly ventilated shafts, mine shafts, for example. The percentage of uranium miners coming down with cancers was much greater than what occurs in a similar population that are not uranium miners. We're also aware there is further data of workers painting watch dials with radium-laden paint. You may recall years ago you could buy a watch, it had dials, and on those dials they glowed in the dark, and that glowing in the dark was the radium, which was a radioactive element, and is a radioactive element. And the way you get these fine paint lines on these dials is you lick the tip of the brush, and then you pass it on onto the dial, onto the hands of the watch. And people who were doing that would get cancers all over their lips and tongues. We have that data. We even have photos of that, unfortunately. The upshot to all this is that we know the effects of high-dose radiation. That is, we know that if the exposure, and I'm just going to make up some numbers here, if the exposure of a given group is 10,000 units of radiation, a certain number of people in that group will develop cancers. If we double the dose, we know that twice as many people are going to come down with those cancers. We know that that information is true for high concentrations. What we don't know is if you're exposed to very low concentrations, and typically the radon problem deals with very low concentrations, if you're exposed to very low concentrations, how many people in a group will develop cancers? That data is not available. There is some data out there, but it is nebulous. It is very thin data. It is not conclusive. So what should we do? Well, we're going to make assumptions about the effects of low-dose exposures based on what we know of high-dose exposures. Now, I think I have this summarized in this next visual, this graph. And what I've plotted here is excess lung cancer rates. That would be lung cancers greater than what we would expect from all other causes versus the exposure to radiation. And in this particular case, we're talking about radon, of course. And the data are the dots that you see here. And we fit a straight line to the data. And you'll notice that that straight line is a pretty reasonable fit to the data. The numbers that you see down here, these are arbitrary units. I don't want you to think they're picocuries per liter or working levels or anything like that. They're just arbitrary units, and this entire graph is to depict what we have found. It looks very much like a straight line fits the data. That is, the data follows a straight line, meaning that if you double the dose, you should expect typically to double the excess lung cancer rates, approximately. But it's very straight line. As you increase the exposures, you increase the number of lung cancers. Gee, that seems reasonable. And by the same factor. Now, however, the problem is you will note that the data only goes down to a certain value. Most of the radon problems, most of the radon concentrations we find in homes are values down here in this region. And there's no conclusive data there. So we have to make certain assumptions. What do you think the rest of this data is going to look like if we had run experiments down here how do you think the data would fit on the graph? Well, one possibility is, as you see here, there's a possibility that the graph could actually curve down and stop at some point, which we would call the threshold. And that is, if this is the way the data goes, and we don't know, but if this is the way the data goes, what we're saying is there is some point below which the radiation does not produce a health hazard. This is not unreasonable in the sense that humans have evolved in an environment with radiation. The sun, the solar energy that we feel every day, that's radiation. There is background radiation, gamma radiation, alphas, betas, cosmic radiation striking us every day. Thousands of pieces of radiation are striking my body as I speak to you now. And we have evolved with that amount of radiation. And so it is possible that low doses may not have any significant effect. That's possible. And this is called the straight line with threshold hypothesis. In other words, the straight line with threshold guess as to what happens at the low dose values. Another possibility that you see on this next visual is that the data, if we were to do the measurements, the data falls along this line here. That is, it just continues along this straight line. And this is the assumption predominantly accepted by the scientific community today. We are assuming that the data in the low doses follow the same straight line, but there is no threshold. That is, there is no amount of radiation which is okay for us, which does not produce a health hazard. And you see, I've summarized that here in the statement. High dose effects indicate straight line, no threshold. And this is the prudent assumption to make. If we operate under this assumption, the worst that could happen is that we're overprotecting ourselves. And that is certainly better than underprotecting ourselves by assuming that there is some threshold, until data comes out to support which one of these might be right. We will continue to go along with the idea of the straight line, no threshold hypothesis. Now you might wonder, well, why don't we do these experiments at the low doses? Well, for one thing, we'd like to do them on humans if we can, and it's difficult to get humans to volunteer to this kind of activity at this point. Also, low doses take 15 and 20 years for them to show up as having produced cancers in the human body. So they're very long studies that require they be done. The radon issue as a home issue has existed for only about 10 years, and so those studies have not been completed. Now I'd like to take a look at some risk estimates due to different kinds of health hazards to establish some perspective on the radon issue. And you'll notice here that because of nuclear power, we lose approximately 0.04 days of our lives. Now I've picked these risk estimates out of different government studies, and if you look at one government study as opposed to another one, the numbers don't all come out to be the same, but that's okay. These are average values, relative values that give us a reasonable handle on what's going on. And what you see here in the number of days, 0.04 days, that's the number of days lost in the average human's life. Nuclear power in this case represents the 109, 10, or 11 nuclear power plants operating in the United States. And because of those power plants, they give off some health hazards, and we lose about 0.04 days of our lives. That's approximately 1 hour of our lives shorter than it would otherwise be. So if somehow you knew that you were going to live 72 years exactly, because nuclear power plants exist, you're going to live 72 years minus 1 hour. That's what this risk estimate tells you. Air pollution costs us 20 days of our lives. Now, of course, if you live in a very polluted city, say on the West Coast, the air pollution would cause a much higher risk estimate in that case. If you live in a very rural area where the air is fresh and clean, if there are such places left, then there would be fewer days of your life lost. But on the average, 20 days of every human's life is lost because of air pollution. If you're immersed in a radon concentration or any radioactive concentration of 1 picocurie per liter over your lifetime, it costs you 100 days of your life. If you smoke 1 cigarette per day, estimates are you also lose 100 days of your life. These two give us some interesting information in the sense that if an individual wants to know what is the health hazard of living, say, in a 4 picocurie per liter environment, then that's equivalent roughly to smoking 4 cigarettes a day as far as a risk estimate, and will cost you approximately 1 year of your life, 4 times what you see on this visual. There'll be more to be said about that later on when we look over the Citizen's Guide. Car accidents, even if you never have an accident, cost you 200 days of your life on the average. This is an easy number to calculate. We know approximately 46,000 Americans die on the highways every year, and we know how many people there are in the U.S., and so you can easily calculate this number to be 200 days approximately. So car accidents cost you 200 days of your life, again on the average. If you're 25 pounds overweight, your life will be shortened by 2 years. And if you live below the poverty line, your life will be shortened by 4 years. If you go into a home and the people are overweight and heavy smokers, and perhaps a little on the poor side, then, and they have a radon concentration of 3, 4, 5, 6, 7 picocuries per liter, the biggest health hazard is in their overweight and their poverty and their smoking. And the best advice you could give them in that case is to stop smoking, lose weight, and get rich. So that's to give you a perspective on the kinds of health risks that are out there every day. Now, how does radon get into the house? It is a soil gas. I guess I've said that plenty of times. And if you look at this drawing, this I've taken out of one of the EPA publications, and you'll see that we have a house sketched here, and the gas can be entering through any one of these pathways. Cracks in the basement floor, utility openings where your electric line or your water line comes in. There's always space there for the radon gas to enter. Overwhelmingly, it comes from the soil and directly into the house. If it goes into the atmosphere first, it will be dissolved long before it has a chance to get into the house. And so if it's going to come into the house, it has to come from the soil directly into the house, bypassing the outside atmosphere. And also, as we will see later on in greater detail, we have a shower here indicating that radon can get in through the shower water. If the house is on a well, for example, if it draws water right out of the ground, well, if there's radon gas in the ground, it will also dissolve into the water. And so when you bring the water into the house, you're going to be bringing the radon gas with it. And it turns out that any agitation of the water allows the radon to escape. And so if you're taking a shower, of course the shower is producing a lot of agitation then to the water, then the radon gas escapes. You're in a shower stall where the radon concentration can be significantly high. And so these are the routes that you should expect radon gas to follow in entering a home. Now finally, I have a graphic from the Pennsylvania DER, as you see here, which gives radon measurements throughout the state pictorially. And you'll see that fundamentally the more hash marks you have, that is, the darker the image appears to be in a given county, the higher the radon concentration. And you'll notice that while there are some in which the concentrations are clearly higher, say in this region here and then down along this area here, there are no regions which are perfectly clear of radon. And in fact, the whiteout regions, the ones that have no hash marks at all, you'll notice, only means there isn't enough data to make a conclusion there. It does not mean that there is no radon there. This is a good place to take a break, and I've placed a set of questions following this visual, and you should see them on the very next page. Now I would like you to go to those questions, answer the questions to the best you can, and then look at the answers in the back of the text and check to see which ones you got right and which ones you didn't. Now for those that you didn't get right, you should look back through the text and confirm that the answer I've given is correct. And then you should return to the video at this place. Now, before you go off, recognize that the video runs several hours, and I don't think you can pay careful attention several hours straight listening to me talk, and we will have some other people in giving discussions. And so I think what you should do is periodically take a break. Maybe watch the video for half an hour and then put it away. Good places to take breaks are where the questions are. After you're done with a set of questions, you may, if you feel tired or having trouble focusing your concentration on this program, put the whole thing away and come back to it tomorrow or later in the day if you like. So don't feel that you have to go through the whole program in one sitting. That would be painful. Do it in small segments, and I think you'll show quite a bit of success. So, again, if you'll do the questions that follow on this very next page, and when you're ready, return to the video at this point, and we'll move along with the program. Thank you.